Another 2.3 word problem. Rancher has this 160 feet of fence. He's trying to enclose three sides of a rectangular field because there's like a river going through one side, and so it won't need a fence on the river side. Find the dimensions of the field with the largest possible area. So he only has 160 feet to use, and he's got to make as much fence work as he can. And it's sort of counterintuitive at first because you figure like, well, 160 feet is going to enclose only so much stuff. But depending on how you configure it, it seems like you can fit more stuff, more area inside, you know. And so I was thinking about this. If you had 160 feet, well, watch this. Okay, so here's the river. Here's basically the idea. He's going to do a rectangular type fence, something that goes out, it comes back the same amount, and then in between here, it's however much you got left to make 160. So all of this is supposed to add up to 160 feet. But that can take different shapes, you know, because you could have a fence where here's the river, and it goes out a bunch, and then goes over just a little bit, and then it comes back, you know, and so most of it's out or whatever. Or there's in-between ground where it goes out some, and over some, and then back, and it's hard to, you know, it's hard to know what the extreme, or what the best way is to maximize the area. Although one thing that seems obvious would be this. You wouldn't want to necessarily make a fence where here's the river, and you go all the way 80 feet out, and then you got to come 80 feet right back. And so both sides of the fence are right next to each other. Then you're guaranteeing that you basically can fit exactly zero things, nothing at all inside the fence. Because it's like it goes 80 feet out and 80 feet back, and that makes the whole 160 feet. And nothing will fit inside there. Or there's another extreme where you'd be like, well, what if you just went out none? You know, instead of not even 1 foot out, you just went all the way across. And that way you could go a whole 160 feet because you don't have to come back with it. But then, like, here's the river, and here's your fence just running alongside it. That would also be a dumb way to ride it, or to make the fence. It would be good to keep people from getting into the river or something, I guess, if they were afraid they were falling in. But nothing can fit inside this fence if it's just running along the river. There's no area inside it. So we definitely have two extreme situations here where there's nothing that can fit inside the fence at all. So we must not have a guarantee of the area inside always being the same. Because certainly it fits some things in here some of the time, but then it fits none over here. I don't know if that makes sense. It's hard to do this in a one-way conversation, so I guess we'll just get started. Anyway, so check this out. If we were to think of that, and let's see if we can try and describe the situation. With these things, it's always best to just draw your way in, see if you can describe the situation, and then we'll figure out the area the best that we can. So if I had this, we have the river, and then, you know, we have a fence that has to add up to 160 feet. It seems like, I don't know how much this is, so I'll put like an X or something. We could put F for foot or something, whatever you want to do, but whatever amount that is, it's rectangular fence, so that's what he wanted to do, and so we're going to add the same amount here, because however much you go out is how much you got to go back. So they got to come back the same amount. What we don't know is how much this is going to be, because we don't know how much we used going out. So if we were to try and make that work, I was thinking about it. If the whole thing's 160, then whatever this is just leftover after using those two sides. So we could say like, let's see here, if we had 160 and this is the leftovers, what if we just said it was like, this is what's left after you take 160 and then you minus off both of those sides. So like minus both of the x's or 2x or something. And then that would be this side. It's the leftovers after you went out and back. Whatever's left from 160 after you used up those sides, I guess. And this would be a way to describe at least the sides of this thing. And what's good about drawing it first is it lets us have a strategy for how to describe the area. And so if we had something like that, we could describe the area being like, well, the area is a rectangle. You know, even though we don't have this side here, we're still enclosing a rectangular area. So we could just say it's base times the height, or length times the width. And so the area with respect to x, if we want to put it in function notation, the area given by these things is the width times the length. So the x times the 160 minus 2x, you know, and we'll just say, even though I don't know how to optimize it yet, what I could say is that at least I know what the area is. or how to describe the area function with respect to the sides that I got. And that's good. And you can leave it like that, or you can distribute it out. It'd be like, what is that, 160x minus 2x squared. Or you could put the 2x squared in front, negative 2x squared plus 160x. Might be whether you're more comfortable with it. Anyway, from there, it seems like if you wanted to make it work thereafter, we could maximize the area by just doing the same old vertex thing, because every time we plug in something in x value, is us just plugging in the number of feet that goes out and back. And then the output of the function, though, you'll notice if I plug something in, the output of the function is an area. And so what we could do is we'll just start plugging in some things, and then once we find ourselves a vertex, that'll probably be our maximum area right here at the output. That's what I'm figuring. So maybe from here, guys, I'm gonna let you do the rest or whatever, but I'll tip you off. Maybe if we did this thing and we were like, well, if I plug in 0, definitely I have 0 area. Which is, that's kind of what our first drawing was, if you remember this thing here. That's if I go 0 feet out and 0 feet back, then I do have 0 area. And then if you do the thing where we take out a common x or something like that, I feel like we can figure out another way to get 0 area. It's probably going to be the other drawing that we did. And so if we do something like that, it would be something like we could take out a negative 2x from both. And then that would leave us with like x minus 80. And then 80 looks like it's the new 0. So that's good. And then we'll just go halfway to that. 80 would be 40, and then plug in the 40, and I think that'll give us the area we were talking about. And so we'll have these dimensions here where it would be like, let's see here, that's 40. So it would be like 40 steps out, 40 steps back. So like the width of it or something would be 40, and then another 40 here, and then whatever this is. And those would be the dimensions of the thing. And then the area would be whatever you get when you times them, which is what we got when we plugged it in. Or this times that, or you just plug the 40 into the function, or here, or there, or whatever version of the function you want to plug it into. That's what I'm thinking. See what you can do with that.